Okay, we'll conclude today with chapter 26 on cosmology. This chapter concerns the Big Bang and the fate of the universe. But cosmology itself actually talks about not just the fate of the universe, but the nature of the universe, which we've already spent most of the of this course talking about, and also the origin of the universe. And it's a little strange, or it might seem a little strange, that we're taking this sort of out of chronological order, because we haven't talked about the origin of the universe. That will actually be in the final presentation, next week's presentation. That'll be chapter 27. But we're looking at the fate of the universe before we actually look. We're going to predict what's going to happen to the universe before we predict, or before we actually talk about what we think happened at the beginning of the universe. We really want to talk about the structure and evolution of the universe, and the Sloan Digital Sky Survey, which is using the Sloan telescope, which is located on Apache Point, the Apache Point Observatory, which is near Sunspot, New Mexico. There's an ongoing program. I think it's I don't know how many more years it has to go, but it's like a 5-year program for surveying as many galaxies as possible. But this is what actually gave us this one structure that I mentioned last time, the Sloan Great Wall. This is a 250 megaparsec long, 50 megaparsec thick filament of galaxies that are approximately 300 megaparsecs from the Earth. And as I mentioned before, it's really the largest known structure in the universe. Now, the Sloan Digital Sky Survey is a wedge type of survey. So, I think I drew that on the board. You can see that on your book. It sort of goes out like that. And there have been 67,000 galaxies that have actually been mapped within 12 degrees of the celestial equator so far. So another kind of survey that's also being done is what's called a pencil beam survey. So rather than progressing out in the form of a wedge, now you've got a narrow kind of a pencil beam. And so what you're looking at is two small regions of the sky that are perpendicular to the galactic plane and out to a distance of about 2,000 megaparsecs. And using that kind of a survey as well just confirms what we're seeing with the Sloan Digital Survey, and that is that there does not appear to be any higher order structure in the cosmos than this Great Wall structure. So when we go out to even greater and greater distances, we don't believe that we're going to see any more structure. So this is really the end of structure in the universe. Now there's something called the cosmological principle, and this consists fundamentally of 2 points. One of them is that space is homogeneous, which means that everywhere you look it's the same. And it's also isotropic, which means it's the same in any direction that you look. And the implication of that, if we accept the cosmological principle, is that the universe actually has no edge, and it also has no center. Now, in the 19th century, there was a gentleman by the name of Heinrich Olbers, and he presented what is sometimes referred to today as Olbers' paradox, although the paradox has been resolved, but it goes something like this. So if the universe, in fact, is isotropic, which is what was believed and still is believed, and it's homogeneous, and it's infinite, well, this is where the problem comes in, because in the 19th century, infinite and unchanging, then for any line of sight, anywhere you'd look, you'd eventually run into a star. So when we look up at the night sky, we don't see stars everywhere. But then again, we can't really see, but if we have a telescope, we're going to see a lot more stars. But the point is that if it's really homogeneous, at any place that you look, eventually you're going to see a star. Okay, so that's the first part of this. And the diminished brightness of very distant stars, because, I mean, as these things get further and further away from the Earth, we're going to expect them to be less bright. But Olber's point was that this should be balanced out by the fact that there's also going to be a lot more stars at these greater distances, because we're going to be looking at a greater area of a sphere of greater radius. So basically, wherever you look in the night sky, what you should be seeing is the sky itself should be as bright as a star would be, maybe even as bright as the sun. But in fact, when we look in any direction, that's not the case. I mean, the sky is basically, except for the moon and the few points of light that we actually are seeing as stars with our naked eye, the sky is pretty much black. It's not. We don't have that. So this created what was called Olber's paradox. If the universe appears to be homogeneous and isotropic, which we say it is, then the assumption that the universe is finite, and or the assumption that it is unchanging, must be false. One of them, or maybe even both of them, are false. But I want to introduce something else right now, which is the age of the universe. So how do we know how old the universe is? Well, okay, again, we can use some very, very basic physics, and we're going to have to rely on Hubble's constant, h sub 0. We know that velocity, this is just fundamental physics, velocity is distance, d, divided by time. Okay? Distance divided by velocity should give us time. Now we also know that the recessional velocity of the universe, which I'll call v sub r, is going to be equal to the Hubble constant, h sub 0, times the distance that any particular object happens to be from us. Okay? So we could then actually substitute in this this value right here for our velocity, and that would give us the time. The time is going to be equal to distance divided by h sub 0 times distance. Well, distance cancels out. That is, it becomes 1. And we get the time is going to be equal to the reciprocal. The age of the universe is actually the reciprocal of the Hubble constant. And what is the Hubble constant? Remember that we said that the Hubble constant was going to be 70 kilometers per second per megaparsec. Well, some of you, and this is the reciprocal of that, so time will therefore be 1 over 70 kilometers per second per 1 megaparsec. And that, ladies and gentlemen, is actually a pretty good approximation of the age of the universe, which we believe to be something right around 14 billion years. So you get that just as the reciprocal of the Hubble constant, which I think is pretty neat. The Big Bang actually resolves Olber's paradox. So the way this works is initially everything was a point, an infinitely dense point, but a point nevertheless. So prior to this primordial explosion, we had an infinite density. The Big Bang occurs. The density and also an incredibly high temperature. Both the density and the temperature start to decrease very, very rapidly. So if the universal age was actually finite, we see only a finite part of the cosmos, and that part within the 14, or as I just showed you now, 13.9 billion years from the time the creation took place. What's beyond that is unknown. The light has not had enough time to reach us, and if the universe continues to expand, maybe that light will never reach us. Stars are also moving away, and they're redshifted, and they're not so bright. So since everything started from a point, no point in space can be the center of the universe. Everything is the center of the universe. And regardless of where an observer is, the Hubble constant is always going to be measured having the same value. So that means the age of the universe, regardless of how we look at it, it's always going to appear to be the same. This is on page 665. But it's kind of an interesting thing why the Hubble constant doesn't change. Because imagine that you've got 5 galaxies that are 100 megaparsecs away from one another. And you're an observer on in one of these 5 galaxies. But when you do the division, you're still going to get 70 kilometers per second, and it's going to be the same thing for an extraterrestrial who's going to be all the way over on the edge. Somebody, let's say, out here, he's going to see 0 here. He's going to see 70 per 100 here. He's going to see 14 per 200 here. He's going to see 21 per 300 here. And out here, he's going to see 28,000 kilometers per second per 400, because that'll be the distance now for 400 megaparsecs. But still, that's still going to come out to the same Hubble constant, 70 kilometers per second per megaparsec. And that number, we say that there's some uncertainty in that number, of course. I mean, we've seen different values. We see some values are calculating, we only get 65. But the point is that I think all the values probably lie maybe within 10% of one another, which means that we could be off when we're estimating the age of the universe. We could be off maybe 1 billion years this way or that way. But the point is that we know that the universe is certainly more than 10 billion years old, more than 12 billion years old, probably at least 13 billion years old, or maybe somewhat older than that, and probably less than 15 billion years old. So we have some range of ages, but we know certainly within a lot less than an order of magnitude, we have a very, very good estimate of the age of the universe. Where did the Big Bang occur? Something else that we might want to consider. And the answer to that question would be it occurred everywhere. And we can use a little analogy of a balloon. We have a balloon, and the balloon is expanding. And what happens is, as the balloon expands, it's only the universe that's expanding, by the way. The balloon, let me just show you this, because I actually, so I've got 3 galaxies that are in proximity to one another, and the Big Bang occurs, and the universe starts to expand. So let's expand the universe right now. Unfortunately, all my other galaxies just popped off. But I can show you with my finger where they are. There's only one galaxy that's actually still left on my balloon. But where my finger is right now, there's actually a white mark here where there was another galaxy that was put in there, and there's another white mark over here. So if you'll have to bear with me here, this kind of makes my demonstration a lot less effective. But you can see, if I can rotate this properly and get it oriented properly with a camera, where these things were only, before I started to inflate this a little bit, where they were only perhaps a half an inch or so away from one another. Now they are much further away from one another. And the one remaining galaxy that's on there, what I want you to see is, it's a bead, obviously, but if I had tried to draw these galaxies onto the surface, rather than actually cementing them on there, even though they didn't stay, what you would have seen is, as I blew the balloon up, the galaxy would have enlarged too. But here you see the balloon has gotten bigger, but the galaxy is exactly the same size, because the galaxy is just really riding on the surface of the balloon. The point of this is that we can now have another, a somewhat different explanation of redshift, and you can see this on page 667 of your textbook. If you have something that looks like this, and it's on the surface of a balloon, this time it is actually expanding with the balloon, you're going to get something that will be a lot bigger. And what's actually happening now is, as this thing expands out, the wavelength, so the wavelength of the emitted light, whatever this happens to be, is going to be red shifted, because as this expands, what that's doing is that's placing more distance between here and here, which means that the frequency has decreased. We're getting less waves per unit time. The energy has decreased as well, and that's shifting the energy to the red region of the spectrum, if we're talking about visible energy. So this is red shifted. So this is just another way of looking at red shift, where we don't have to invoke a lot of the other things that we invoked before, but we can just say that red shift is a natural conclusion of the fact that the universe is actually expanding. So the cosmological redshift can be explained in the same way as I explained the fact that the galaxies are getting further away from one another. As the universe expands, we're just getting a longer wavelength. The fate of the cosmos, and that's really what the remainder of this chapter is about. What's going to happen to us? Where do we go from here? So we're at a point right now where if we could actually go back to the Big Bang, we're at a point right now, at a time where a couple different curves are actually intersecting with one another. So we could look at a couple different fates for the cosmos. We could look at one where, depending on the density of the cosmos, if we were to look at the density of the universe overall, depending on what it is, that's going to determine what the ultimate fate of the universe is going to be. This idea of what is known as the critical density. So for a Hubble constant, 70 kilometers per second per megaparsec, it turns out, and that what we're going to see is this number, which is called rho, which is the density, rho sub c. This is equal to the critical density. And the critical density of the universe, which is an important number, is actually equal to 9 times 10 to the minus 27th kilograms per cubic meter. It actually corresponds to about 5 hydrogen atoms. This is approximately equal to the mass of 5 hydrogen atoms per cubic meter. So that is a critical value, and that's an important value as well. So this is it in a nutshell. And that actually, if you wanted to put this on a much larger scale, this would be equal to about 1/10 of the mass of the Milky Way per cubic megaparsec of space. So it's still, the cubic megaparsec is an enormous volume of space. So 1/10 of the Milky Way, I mean, you'd say the Milky Way is pretty big, but it's nothing. It's still like 5 hydrogen atoms in a cubic meter. So we call it a rho. So I'll call rho sub A is the actual density. And so there's three possibilities. One of them is that the actual density is greater than rho sub c. We could also have the actual density equal to rho sub c. And the last possibility is that the actual density is less than rho sub c. Okay, so each of these implies a different geometry, and each of them also implies a different fate for the universe. So in the first one, the actual density is greater than rho sub c. And in this particular case, the universe experiences what we call a heat death, and sometimes this is referred to as the Big Crunch. What this means is, if the actual density of the universe is greater than this, gravity is going to be the overriding force. And eventually the universal expansion is going to come to a halt. Gravity is going to slow it down. It's going to get slow. The universe we know is expanding right now. It's going to expand slower and slower. And eventually gravity, which of course is weakening with increased distance, but if there's enough matter in the universe, eventually gravity is going to start to pull everything back in again. And then everything goes back to that initial point again, and the universe is destroyed in a big crunch. the antithesis of the Big Bang. And we actually call this closed space. One is that these two values are exactly equal, and that would be a flat space. The third possibility is that the actual density of the universe is less than the critical value, and this is open space. Now, what do these things look like? Well, closed space looks like what I was showing you before. I blew it up. It was a ball. It was a sphere. A sphere, in this particular instance, we say, in this particular instance, space itself would have a curvature, kind of a spherical curvature. And so we've got somebody up here, and this little guy is shining a flashlight. And he shines his flashlight out in this direction, because space is curving like this. Eventually, after an extraordinarily long period of time, the beam of light comes back and hits his back. So this is curved space. This is also called Riemannian space, after Georg Riemann, who was the one that actually proposed this particular model. And it's an easy model for us to visualize. Flat space is Euclidean space. So this is Euclidean, or we could call it Newtonian space. This is the space that, at least locally, that we're familiar with. In flat space, in Euclidean space, a triangle. I'm going to make an equilateral triangle. An equilateral triangle has 180 degrees. 60 degrees here, 60 degrees here, and 60 degrees here. But if we've got closed space, if we have a sphere, then if we actually put triangles on it, what we're going to find, and I want to show you this because I actually made a little model of this. Here's our closed space model, and you'll notice what I've attempted to do, as best as I could, is to try to draw a series of right triangles. There's one there, so I'm going to put my finger over. Let me see. The one that you're looking at is right over here. I've got another one over here. Again, you can see it's a right triangle. And then I've got a third one right over here, another right triangle. See if I can get that into view. And there's another right triangle. And I've drawn straight lines. And actually, they all connect. And you see that my triangle appears to have actually curved sides. Even though they're straight lines, if I hold them in this fashion, on the surface of the sphere, they actually appear as curved sides. So what do I have now? I have a triangle. I have an equilateral triangle. But nevertheless, for my equilateral triangle, what I've got is a triangle that now actually has, because there's a right angle here, and there's a right angle here, and a right angle there, my triangle, rather than being 180 degrees, is a 270 degree triangle. Kind of a strange triangle. But that's what we have in closed space. Now, in the last instance, in open space, so this one, as I said, this is called Riemannian space, after Riemann. So this is Riemannian space. Down here we have what's called, this is named after Nikolai Ivanovich Chpt, another 19th century mathematician. I don't know if I can spell Lobachevsky's name correctly. Lobachevsky, something like this. It would be in Russian anyway. But this is Lobachevskian space. And what that looks like, and that's a little bit harder to visualize because we can't really make a model in the same sense that we can make a spherical model, but the closest approximation we can come to is a saddle. And there, the sum of the angles is going to be less than 180 degrees. So that's going to be characteristic of what we would see in Lobachevskian space. So everything really depends on the ratio of P sub A, rather rho sub A, to rho sub C. That is the actual density of the universe compared to the critical density. And that becomes, introduce a new term, which is called omega sub zero, which is pronounced omega naught. And it's equal to, as I said before, rho sub A divided by rho sub C. If omega naught is greater than 1, space is curved so that we've got that spherical curvature. I already said that. That is a closed universe, and I said that as well. But that universe is finite in extent. If omega naught is less than 1, this is the low density open Lobachevskian universe. The universe is going to be infinite. If omega naught is equal to 1, it's also going to be infinite, but it's going to be flat. And that flat universe is called the critical universe. And this is as I say, is a Euclidean or Newtonian type of universe. So we really, in order to really answer this question, we really need to know what else is in the universe. I mean, we looked at matter, luminous matter, dark matter. There's also energy, which has we can convert the energy into matter using Einstein's equation equals mc squared. So we can take anything that's in the form of energy and get its matter equivalent. But when we do that, it turns out that we're still going to be losing a lot of matter from what we think should actually be out there. What the value, if we include dark matter, if we leave dark matter out of the equation altogether, we only get about 1% of the critical density of the universe. If we just look at luminous matter, we're only going to get about 1%. But if we factor in energy and if we factor in dark matter, we're actually going to get up to about 25% roughly of the of criticality. So that would be omega naught equal to about 0.25. Now, if that's all there is, then that would imply that we've got a universe, since omega naught is going to be less than 1, that would be a finite closed universe. And that would be that first instance where you shine the flashlight away from you and it comes back and it hits you again. And in billions of years from now, the universe is going to collapse into a big crunch. However, we still haven't talked about, well, we talked about it, but we really haven't said anything about the effect of dark energy on this. So if we look at everything else, we're still missing 3/4 of the mass, or the mass equivalent that we need. In some regions of space, there are inhomogeneities. And by observing how the local group of galaxies moves within the local supercluster, it appears that a large accumulation of mass, maybe as much as 10 to the 17th solar masses, it's about 100 to 150 megaparsecs in size, is actually affecting this motion. And so there is something else out there that's called the great attractor. And this great attractor, it itself appears to have a critical density of around 1. However, if we take the great attractor and add it into everything else, we still only get omega naught up to about 0.30. So we still have that problem of about 70% of missing mass there. But again, we've got the dark energy to consider. Independently, the density of the universe can be arrived at by determining cosmic acceleration. And the universe is universal expansion is accelerating, and you can actually do a plot. But what I wanted to show you is if you plot distance and redshift, you get something that looks like this. And this is showing us that the universe is expanding. We actually, I mean, there's 3 possibilities here. If the universe were moving at constant, the universe were moving at constant velocity, what we would see is a line that all of our galaxies and everything that we're looking at would fall somewhere along this line. Down here, everything is pretty much over, along that line. But when you get out to distances somewhere in the thousands of megaparsecs, you start to get some divergence occurring. And there's a couple possibilities. One of them is if we saw divergence along this line here, so if it started to curve upward, that would actually indicate that that acceleration was slowing, that we actually were starting to see negative acceleration. So the acceleration is starting to slow down. Your book calls this deceleration. I don't like the word deceleration because it's not really a physical term. We talk about negative acceleration for slowing down, but I'll use the term deceleration. And then on the other side here, if it's actually speeding up, then we're getting acceleration. And when we do these plots, we see that galaxies are most of the galaxies are falling along that line there. So that seems to imply an accelerating universe. The universe is expanding and it's accelerating. And something is at work that's opposing gravity, because gravity is what would be operating up here that would cause the deceleration. So what is opposing gravity? This is what we call dark energy. And as I said, we don't really know what it is, but there has to be something out there that is actually opposing the expansion of the deceleration or the contraction of the universe, if you wish. And this force, which has nothing to do with matter, it's not matter, it's not radiation, it's of unknown origin, but it's repulsive in nature rather than being attractive as gravity is, and we call it dark energy. It also has, sometimes is referred to as vacuum energy. Anti-gravity is another term that's thrown around, and sometimes referred to as the cosmological constant. It was actually something that Einstein originally threw into his equations because he was trying, it was sort of like a fudge factor that he put in because he assumed that the universe was not expanding, and he put this factor in there to make everything come out in the right way. And it turned out when it was found that the universe was in fact expanding, Einstein said, well, that was like the biggest mistake that he ever made. He took that out of the equation, and what's actually happening is it's starting to creep back into equations now because there's some evidence that there is this cosmological constant. It might not have exactly the same value that Einstein suggested, but it probably does. It's probably very, very close to that. So as the universe expands, the gravitational force is slowing, acceleration is weakening, and dark energy, which is hastening the acceleration, is actually starting to increase. Vacuum energy is actually associated with empty space, and it's only effective on a very, very large scale. Another candidate for dark energy is something called quintessence. And again, these things are not really very, very well defined in terms of things that we can talk about. I mean, there's mathematical definitions of them, which would be beyond you. But where the point I want to make is that while the cosmological constant, that is the vacuum energy, is always constant throughout time, the idea of quintessence is it's something that can change and has changed through time. And it can be attractive or repulsive depending on the ratio of kinetic to potential energy in the universe, which actually has changed as the universe has from the time of the Big Bang to the present, and will continue to change. So about 10 billion years ago, quintessence, it's believed, actually became repulsive. It was attractive up until that point in time, up until the universe was about approximately 4 billion years old, and then after that, it started to repel everything. So if we take dark energy estimates, everything that we have, and we add that into omega sub 0, that's going to give us a value of, we had 0.3 before, and that's going to give us the other 0.7 that we need. So luminous matter is about 4% of the matter of the composition of the universe. Dark matter about 23%, and dark energy the remaining 73%, giving us an omega naught of 1, which supports a flat, infinite universe that is going to continue to expand forever. So so that's what the current theory is. Now, that may also seem to be a little bit, depending on how you read this, you might think, well, isn't that a contradiction? Didn't Einstein say that space was curved? So how can the universe be flat? Well, no, that's not really what Einstein said. What Einstein said was that massive objects will curve space, but they do so only locally. So space itself can be flat overall. You know, we can think of it as an infinite sheet, space-time, drawing boundaries to it. But if we can look at it on the side, you see it as being flat. Whenever there is a, let's say there's a black hole in there, we're going to get this kind of depression. We might have a galaxy that's going to cause something like that to happen. But the point is, these are little local inhomogeneities in the flatness of space. So space overall is flat, but it is curved in the regions where there's concentrations of matter that will cause a kind of local curvature. If we're correct, it's going to be a universe that will continue on forever. I mean, the Earth will be destroyed long before anything else happens to the universe. The universe will continue to grow. Things will get further and further apart from one another, but we'll still have the universe will still be here. It's not believed that it's going to curve in on itself and crunch us out. One other thing that I wanted to say: cosmic microwave background radiation, and this was kind of interesting because the gentleman who won the Nobel Prize for discovering this, when they first observed it, kind of a hissing sound that they were getting through their radio telescopes. At one point in time, they thought it was actually due to pigeons. They weren't really sure what it was, but it didn't matter what direction they pointed the radio telescope. They always got this same hissing noise. And ultimately, they came to the realization that what this is this is the energy that pervades the entire cosmos in all directions. It's in the radio frequency because the energy really is going to depend on the temperature of the energy, the temperature of that particular perturbation. So, for instance, something like 1 second after the Big Bang occurred, the temperature of the universe was enormous, and the universe was at that point was just dominated by radiation. That's all we had. So at 1 second, all we really had was, and this, what I'm attempting to show here is a black body curve. So this is intensity, and this is the frequency of the radiation. But it's also a function of temperature as well. So this is at higher temperature. So at 1 second, all we had was gamma radiation. And after approximately 100,000 years, the universe had cooled off enough that temperature is a little bit less. We've got a black body curve that's going to look something like this. So something like that. And at this point in time, the universe is, so the frequency has decreased somewhat, and we're going to get a different. So this is gamma. Now at this point, we're probably going to be something maybe in the. This is probably in the UV region. Then after another period of time elapses, get another black body curve that looks sort of like that. This is 10 to the 7th years. This was 10 to the 5th. This is 10 to the 7th, so that's 10 million years. After 10 million years now, the universe has cooled off enough that now we're going to start to see visible light. And then today, we're up in the 10 to the 10th region. It's say 1.4 times 10 to the 10th. And now what we're seeing is, everywhere we look, is we're seeing something that we would expect at a temperature of 3, that corresponds to a temperature of 3 kelvins. And this is the background, this is the cosmic background radiation. So this is the energy that's left over from the Big Bang after nearly 14 billion years. Now the universe is cooled to the point where overall the radiation that's coming out is coming out at 3 kelvins, and that corresponds, of course, to radio waves. I believe that concludes what I want to say about the fate of the universe. So anyway, thanks again for your attention.